particle man, doing the things that a particle can. What's he like? It's not important, particle man. That's it. That's the intro. Hi, and welcome to episode 3 of Living as Nature, where a non-scientist draws on science in an attempt to develop a better philosophical understanding of our place in the universe. Today, we're going to talk about particles, atoms, and stars. Yeah, Carl, I know there's a bit of a size jump between those last two. I can't do everything. We need to begin with a disclaimer. It's tempting to hear a word like particle and atom, picture the models and images we've seen in textbooks, and think, well, that's exactly what those things really are. But the way we sometimes describe things like particles, for example, the building blocks of the universe, and the way we depict things like atoms, don't necessarily cohere perfectly with what they actually are. For example, there's a debate regarding whether particles are better understood as points of matter, or waves resulting from excitations of underlying quantum fields, or perhaps both. We're not going to focus on that here. And thank God, Carl. I've already said more than I understand about it. But it's good to remember that we're dealing with imperfect language and model representations that are still in development. Also, it's good to remember that we're selectively exploring and simplifying complex concepts. That said, let's consider some things about particles. It might be helpful to create some basic categories to discuss particles. To understand these categories better, we should establish some terms. An atom is the basic unit of an element. So you can have an atom of hydrogen, an atom of carbon, an atom of magnesium, and so on. Atoms can bond together. We'll talk about how they do this in a later video to form molecules. For example, 2 hydrogen atoms and an oxygen atom form a water molecule. If 8 carbon atoms, 10 hydrogen atoms, 4 nitrogen atoms, and 2 oxygen atoms bond together, that's a real party, Carl. I'd like to be involved in that. You got yourself a caffeine molecule, and you're ready to face the day. Molecules can form more complex things. We'll say more about this in future videos as well. My mouth is writing checks that my future mental state might not be able to cash, Carl. Just saying. Science textbooks often use the term subatomic particles, which refers to particles that are smaller than an atom. More generally, the word particle might also refer to a molecule, a particle of dust, and so on. But in particle physics, the word tends to refer to subatomic particles. Among subatomic particles, there are 3 that make up an atom: protons and neutrons, which form the nucleus of an atom, and electrons, which, for lack of a better term, orbit around the nucleus. But these are just a few of the subatomic particles at work in our universe. Today, physicists tend to use what's called the standard model of elementary particles to map what are referred to as fundamental or elementary particles. That is, particles that don't seem to be made up of smaller things. It looks like this. I like when we're in sync, Carl. I like it. Here you have quarks, leptons, and bosons. I mean, were these named after like famous clowns? Oh, boson and quirky are fighting over who gets the best nose again. Quarks and leptons are referred to as fermions, and they make up all matter as we know it. They come in a variety pack, like those little packets of cereal you used to get when you were a kid. They always snuck some horrible cereal in there, Carl. You'd go home, devour 4 tasty cereals, and then be stuck with cornflakes and some ungodly raisin concoction. Leptons include our friend the electron, but also muons, taus, and neutrino variations. When it comes to quarks, you got up quarks, down quarks, charm quarks, which I think have marshmallows in them, strange quarks, top quarks, and bottom quarks. Quarks make up protons and neutrons, 3 quarks in each case. A proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. Bosons are really interesting because they function as force-carrying particles, facilitating the fundamental forces, or interactions, we talked about in the last episode. Gluons carry the strong nuclear force. And, as I said in episode 2, if we didn't have the strong nuclear force, we wouldn't have protons or neutrons. And if we didn't have protons or neutrons, we wouldn't have atoms, no molecules, and no life as we know it. Photons, or light particles, carry the electromagnetic force, and W and H bosons carry the weak nuclear force. If you're paying attention, you'll notice there isn't a boson in the standard model designated to carrying gravity. And that's one shortcoming of the current standard model. It's incomplete. We just don't have a way of making sense of gravity that accounts for both Einstein's theory of relativity and quantum mechanics. If you're able to figure that out, and get credit for it, you'll be pretty famous. Again, I'm leaving a lot out here, including antimatter and the more recently discovered Higgs boson particle, which is responsible for giving other fundamental particles their mass. Okay, so that's a simplistic picture of elemental particles. Bosons carry the fundamental forces. Fermions provide particles of matter, such as up and down quarks and electrons from the lepton menu. Up and down quarks form protons and neutrons, which together form the nuclei of atoms. Add some electrons and electromagnetic force, and you have an atom. So how did all these little particles come about? Let's tell this story using a standard Big Bang model followed by a period of inflation. Just remember though, there are inflation models that put the period of inflation before the Big Bang. At first, the universe is too hot and energetic to get particles like protons and neutrons. You do, however, get your bosons. Get your boson, get your boson. It's like a Missy Elliott song, right? And after that, some quarks and leptons taking shape in the immense heat. As the universe rapidly cools, because it's expanding, quarks chill out enough that they can link up to form protons and neutrons. All of this happens within the first second of the universe's existence. It was, pretty arguably, the most radical second in the history of the universe. But there's a problem. Well, there's a problem if you want matter to hang around and build complex things. Matter isn't alone. There's someone else in the house. It has a roommate, antimatter. And like that college roommate who stays up late listening to loud music, snores like a bear when they actually do go to sleep, and then hits the snooze 17 times before they actually wake up in the morning, antimatter makes things difficult for matter. In short, they're at war. Metaphorically speaking. As matter forms, antimatter forms. And when they meet, they annihilate one another. On a positive note, this process creates photons. Nice. This goes on until about 3 seconds into the story. And, thankfully for us, when the dust settles, there's a remnant of protons and neutrons in the universe. And all the matter that we have comes from that remnant. As the universe continues to cool, these protons and neutrons are able to fuse into the nuclei for hydrogen, 1 proton and 1 neutron, and helium, 2 protons and 2 neutrons. There's more hydrogen than helium, a ratio of about 3:1, and that's still pretty close to the case. Today, hydrogen and helium make up about 98% of the elemental composition of the universe. When these first nuclei form, we don't have any atoms yet. It's still too hot for that to happen. But we're only about 3 minutes into the universe story, so there's still time. For a long while, about 380,000 years, the universe is a soup of matter, a foggy plasma that scatters light. At about 380,000 years, the universe cooled enough for the first hydrogen and helium, and just a little bit of lithium, atoms to form, when the electromagnetic force coupled negatively charged electrons with positively charged nuclei, which contain protons. When this happened, the foggy plasma dissipated. The universe became transparent, and it was very, very dark. Now we have a universe with a lot of hydrogen, and a lot of helium. And all this is driven, in part, by the 4 fundamental forces, or interactions, we discussed in the last episode. The universe continues to cool, and some denser regions of hydrogen and helium gas collapse in on themselves under gravity's pull. The more they do so, the stronger the gravitational pull they exert, creating a sort of domino effect. As more and more atoms pile on, pressure grows, and temperatures greatly increase. In time, the temperature at the core gets so hot that nuclear fusion begins. The nuclei of hydrogen atoms are fused together to make helium atoms. When this core ignites and nuclear fusion begins, we have a star. By this process, the first generation of stars, called Process 3 stars, formed. We're now at least 100 to 200 million years into the universe story. I told you we'd go faster than last episode. We're just scooting right along. These stars are absolutely crucial to the development of further complexity because of nuclear fusion, which, if you recall from episode 2, is made possible by the weak nuclear force. Now, remember that at this point, the elemental composition of the universe is just hydrogen and helium. But in these stars, through nuclear fusion, new elements are going to emerge. Let's talk about stars. I know someone watching this is like, oh my god, we're just getting the stars? I thought we were wrapping this up. Not all stars are the same. They vary in mass, color, temperature, luminosity, and so on. Astronomers classify stars using a system of letters. O, B, A, F, G, K, M. O stars are the hottest and burn bluish white. They also tend to have the largest mass. M stars are the coolest and burn reddish orange. They also tend to have the smallest mass. There are subcategories within these letters ranging from 0 to 9. So, for example, a star between F0 and G0 would be classified as an F5 star. Our sun is classified as a G2 star. So, on the smaller, cooler side, and tending toward the orange-red color spectrum. Stars also have a life cycle. Stars form from nebulae, which are dense clouds of gas and dust. Think of the dense clouds of hydrogen and helium from which the first stars formed. around. Gravity causes these clouds to collapse in on themselves, forming a protostar. As gravity continues to pull matter into the core, and the protostar significantly heats up, the nuclear fusion of hydrogen into helium begins. It's now officially a star, and it's on what astronomers refer to as the main sequence. The main sequence refers to the period in which stars are fusing hydrogen into helium in their cores. Astronomers estimate that about 90% of all stars in the universe are on this sequence. But when a star exhausts the hydrogen in its core, it departs from the main sequence. Depending on its mass, the star will either become a red giant, if it's a smaller star, or a supergiant, if it's a bigger star. During this phase, the star expands to a much larger size. It begins to fuse helium into heavier elements such as carbon and nitrogen. The most massive stars can fuse elements as heavy as iron, but that signals the end of the life of a star. Red giants eventually blast their outer shell into space, creating what's called a planetary nebula. The star itself becomes a white dwarf, which is a very dense, hot, and dim star. When I say it's dense, I mean to say that a teaspoon of white dwarf material would weigh 5.5 tons on Earth, or roughly the weight of two very large Ford F-150s. We get elements that are heavier than iron from massive stars that become supergiants. Supergiants don't just die. They go down swinging in spectacular events we call Type II supernovas. This happens when the iron in their core collapses under the pressure of gravity. There's also a Type Ia supernova. Check the links in the description out for more information on this type of supernova, which requires a binary star system and a white dwarf. A supernova is a stellar explosion of immense power, as in several times this many warheads. When a star goes supernova, it creates a massive amount of energy, permitting the fusion of heavier elements, such as gold, silver, lead, uranium, and mercury. It's interesting to think that, if you're wearing gold or silver jewelry, the atoms in that jewelry were created in a supernova. When these stars explode, they scatter these heavier elements across the universe, providing the seeds for new stars, as well as galaxies and solar systems. When a supergiant dies, it can become either a neutron star or a black hole. A neutron star is even smaller and denser than a white dwarf. A teaspoon of neutron star would weigh closer to 1 billion tons on Earth. It would be heavier than Mount Everest. Black holes are immensely interesting. Their gravitational pull is so strong that not even light can escape it. There's evidence that black holes are key to the formations of galaxies. There's actually a black hole in the middle of our Milky Way galaxy. Alright, let's summarize. Thanks to the order of our universe, including the four fundamental forces, or interactions, and the bosons that carry them, we get the fundamental particles of matter, quarks and leptons. These make protons and neutrons and atoms possible. The first atoms in our universe, hydrogen and helium, formed the first stars under the pressure of gravity, and with the help of the weak nuclear force, which makes nuclear fusion possible. The fusion that occurs in various stars produces heavier elements, such as carbon and nitrogen. These heavier elements, among other things, make other stars, planets, galaxies, and solar systems possible. We'll also find that they make life possible. For example, the hydrogen in human bodies came from the earlier stages of the universe. You have atoms in your body that are over 13 billion years old. The heavier elements in human bodies, carbon, nitrogen, iron, and so on, were fused in the nuclear furnaces of stars. This is where you get the expression, "we are made from stardust." In a poetic sense, when you go out at night and look up at the stars, you are staring at your cosmic family tree. That's how connected our stories are to the story of the universe. I hope you found this video enjoyable. In our next video, we'll discuss the formation of our sun and the planet Earth. Until then, farewell. Is he a dot or is he a speck? When he's in water, does he get wet? Or does the water get him instead? Nobody knows. Particle Man.